Hi guys, in this video I'm going to go over the solutions for the practice exam 2. So before I start, I want you guys to at least spend some time trying over all of the problems. Okay, so let's go over starting problem 1. So problem 1, this problem asks you guys to prove that this is a true statement, and I wanted you guys to do this without using the truth table because I think we had a good amount of practice using the truth table for exam 1. Okay. So how to do this without the help of our truth table, which is always fun to create, is we're going to utilize these logical equivalences. Okay. So you have all of these options that you guys can use, but for the first problem, I'm going to utilize, I think, the first equivalence and this one. Okay, so let's go back, and there are multiple ways of proving that this is true. So you could have a different solution or different process, but still get to the same solution. Okay, so I'm just going to write us down the two statements that I'm going to use. The first one was not if P then Q. And this is identical to P and not Q. Second one is if P then Q, then that's the same thing as not P or Q. Okay. All right, so for the first step, I think I'm going to utilize the second one I've written because I see that at this entirety, if you look, it's this one, if the first part, then not Q. Okay. So kind of pretend that this whole thing on the left-hand side of my right-sided arrow is P, and not P is just Q. All right, and in that case, this is identical to negating the first part, the left-hand side, which is Q and if P, Q. And this should be conjoined by or, and just Q just gets followed by Q. So in this case, it's not Q for us, but it's not P, so I'm just going to copy that down. Okay. All right, the next step, I also notice that I have another if P then Q statement. So I can substitute this with not P or Q. Okay, and I can do that, and also the negation. If I negate the whole thing, so I'm probably going to use, I think the rule of negation is on the other page of your textbook, but it's, so do that. So negation and negation of Q, that just becomes Q, and this and symbol becomes or. And negation of this, but instead of if not then Q, I'm going to use not P or Q, and I'm going to copy what I have remains. All right. I think I can distribute the negation sign here again, so that becomes negation, and negation of P becomes just P, and negation of or becomes and negation of Q becomes negation of Q, P, like that. Okay, the next part, I'm going to do this. So this is going to be a distributive rule, or I think in the textbook it uses the De Morgan's rule. So that becomes Q or P and Q or not Q. And I still have the remaining things that I have to copy. All right, and now I take a look at this. Q or not Q. So that's a total tautology statement. Let's see if I don't have it here. So this is T, and I have, I'm just going to change to copy. Okay. The next part I'm going to do is this. If you have something and a tautology within the end statement, and again, go back and check all these rules on your textbook. It should be under section 1.3. Then it just becomes this, the first part. So it is Q or P. And I'm going to copy down the rest, P. All right, so in this case, now I'm going to do similar to our this step. I'm going to take a look at this. So that part becomes, you can still continue to take the parentheses, and you can take the next step using the associative rule and do this. All right, so now this part is another T. So I have Q or T. Again, Q or T, that just takes on the Q part. Because we are solving this under the assumption that P and Q are true, we ended up at something that is with a true value, so therefore we have proved that this is a tautology. All right, let's go ahead and take a look at problem 2. Find a counterexample, if possible, to these universally quantified statements when the domain for all variable consists of all real numbers. Okay, so I think for A, finding a counterexample is pretty easy. I think this case, what if x equals to 0? If x equals to 0, then we do have a case that 0 squared equals to 0, which is true. So this just one counterexample justifies that this cannot be true. And because of this for all statement, that's not true. All right, for B, all real numbers. Okay, so what if I say, let's pretend that this works. Okay, then let me put square roots to both sides. That comes with plus and minus. So that would be my counterexample. What if x is plus or minus square root of 2? Then, if I take positive root 2 or negative root 2, then by squaring that number, I do get positive 2. So therefore, because of these counterexamples, so we have two cases, B is not a universally quantified statement. Okay. And this is only true because my variable, it's stated that the variables consist of all real numbers. If it said this is all positive integers, then this will not be true. Okay. All right, so let's take a look at C. For all, that this must be always true. Okay. But what if I have x value as 3 or negative 3? Is this true? This is not true. So therefore, 3 is an example. You can get a lot of numbers. So it's basically if x is between 10 and negative 10, it could also be equal, then these are all the counterexamples of C. So you can give me any specific number because it asks for just give one counterexample. So for C, you can give me x equals to 3. If x equals to 3, then since the absolute value of 3 is not greater than 10, this is a counterexample of C that proves that this is not a universally quantified statement. Okay, all right, let's go for number 3. Express the statement there is a number x such that when it's added to any number, the result is that number, and if it is multiplied by any number, the result is x as a logical expression. All right, so it seems like we need two predicates. The first one is the part where x is such that when it is added together, to a number, then the result is that number. So let's go ahead and figure that out. So I'm going to call this as P it seems like I need two variables because, of course, I need x, it's our given, and it's saying that it's added to any number. That any number we don't know, so I'm going to call it y. Okay. So this statement can be written as when x is added to any number. For our case, we decided to use y. Okay. And sorry, this should not be equal. It should just be. Okay. Then this is going to equal to that any number, which is y. Okay, so we have that part. Now let's take a look at the second statement. If it is multiplied by any number, then the result is x. So we have used p, so now let's use q. And we're still using two variables, which is x and y. And the statement is going to be such that if x is multiplied to any number y, then the result will be x this time. Okay. Now, since we have defined p and q, we can go ahead and write our logical expression. So there exists a number x. So I'm going to use there exists x. Okay, so there exists that symbol, mathematical symbol is like the big E, but reflected. There exists that y should be any number. So any number meaning for all y, okay, p xy satisfies, and this is conjoined by and q xy satisfies. So this is going to be our answer for problem 3. So problem 4, we have to express the statements. The first one is everybody loves Raymond, B is everybody loves somebody, and C is there is somebody whom everybody loves. So it seems like we need to come up with the predicate of x, y, and our first job is to define this. And I'm going to define this as x loves y. Okay. And it's important that we also state our domain. Our domain is x is going to be part of all the people in the world. So all people in everyone in the world. Okay, so after we define this, we can go ahead and use p xy because we have defined it. So everybody loves Raymond. So for this case, our x should be, that somebody should be everyone, so we're going to have to use for all x. Okay, so for all x, there's going to be a case where x, everybody, loves Raymond. So x comma, in this case, instead of y, we're going to do Raymond. Okay, so that's done. Let's go ahead and take a look at B. Everybody loves somebody. So again, we're using everyone, so that's going to be for all x. Okay, so for all x, there's going to exist someone, right, that they're going to that we love. So there exists someone that such that p x y. Okay, so that's the expression of B. Let's go over our last part. So there is somebody whom everybody loves. So there is someone, that's going to be there exists statement, and whom everybody loves, I can go, that someone is that something that we don't know yet, and everybody loves that exact someone. So everybody is the x, loves someone, that y, so we're going to do there exists y. And for all x, this predicate is satisfied.